What is light? Where does light come from? We know light comes from the sun as our primary light source. We have light from light bulbs as well. We know that sunlight is in fact white, and we know light is connected to color. So even though in a beautiful day you might see all kind of colors, right? The yellow, the blue. In some days it's just blue and bright white. Other days it's yellow sun and orange, red environment, sky, clouds. That's because what we see in the visible spectrum with our eyes is red, orange, yellow, green, blue, indigo, and violet. Red, green, blue is what our eyes see the strongest. So in a more technical term, this is part of the electromagnetic spectrum. So all of these beams and rays, or wavelength as they call it, these are visible to our eyes. So you've probably heard of radio waves, ultraviolet, infrared, gamma rays, you know. If you listen to a radio or even your mobile phone, it doesn't matter. You don't see waves, you don't see the colors, you don't see what's going on around you, but they exist nonetheless, they are there. So, unless we use certain technologies, we don't really see X-ray, right? You can see through the bones. Infrared, you can see through the walls, and you can see people, heat wave signals, all of this. We have some technologies that allows us to see this kind of wavelengths. So, but to us, what we can see with our human eye without technology is the visible light, right? Red, orange, yellow, green, blue, indigo, and violet. These are the same colors which are in rainbow colors, but together they make the color white. That means red, green, blue are the primary colors. Red, green, blue are the primary colors in what we call additive colors, which is what we use. When you combine these three, you can see it creates yellow, cyan, and violet or indigo. If I take away one, I lose white. In the same way, that is how the environment works. To simplify it without going into advanced physics or math, when the sun is closest and the light travels the shortest, blue light are more scattered due to the dust particles. So basically the sunlight is on a straight line, right? It's not in an angle. But when it goes down, further down, it has a shorter distance and angled is differently. The blue wavelength has the shortest wavelength, right? It has the shortest wavelength here. And red and orange has the longest wavelength. So basically what happens when the sunlight is on a different angle further down, it mixes more with the dust because the longest wavelength survives longer, and you end up with more orange and red. Keep in mind this is a very simplified explanation, just to give you an idea of how light works. Now you might be asking, but hey, Amit, the shortest wavelength is actually violet, so why don't we see violet? Well, that's because, as I said, the cones, the color receptors or cones or retina in our eyes, they pick up red, blue, and green the most. So we're actually quite bad at noticing violet in general. But it's good to know that our eyes are very sensitive to color and details, so that's why we edit images to replicate what the eyes see, because the camera doesn't actually have the same ability to see things identical to what we see. That is why we edit exposure and levels and saturation in Photoshop or Lightroom or whatever software you choose when doing photography. Birds, however, they say 4 primaries instead, while mammals use 2 primaries. So they will see things differently than us. So it doesn't mean things are exactly the same for every other creature on the planet, but this is what we see and this is how we understand it. The rainbow, however, happens due to refraction. And there are things that happen with light when it hits a certain surface. It's reflection, refraction, and shadow, for example, are some of the things that happen, and we will be talking about it closer later on. But I want to end this video for now that, did you know that humans are bioluminescent, which means we emit light as well. But it's so weak compared to everything else, and compared to what we are able to see, that we don't notice with our human eyes that we project light and heat. But we know we do it due to technology. So with that, I'll see you on the next video. So, light is not just color. It's not just red, orange, yellow, green, blue, indigo, and violet together making white. Right? It's not just visible light. Other things occurs with the light, which is also refraction. And that is basically what happens when we see the rainbows. The rays from the sun that are hitting raindrops. And that's why we call it a rainbow as well, because the light enters these drops of water and they get twisted and turned because they go from one surface to another surface, then they come back out of the water drop and they have twisted and turned again, and in a massive scale we end up seeing the rainbow, which is part of the visible spectrum. So to explain it a bit easier or simpler, the refraction of light is when light bends as it travels between two different surfaces. So in this context, when I say surface, I do not mean only visible surface. It includes air and water being two different surfaces. So when light hits the first surface and is about to enter the second surface, for example between air and glass of water, or in this case a cup of tea, an incident medium occurs. This is when light refracts, called refractive medium. So basically, looking at this example, you can tell that the spoon is really somewhere around here, but we are noticing the spoon over here, or more accurately over here. So something is happening. Well, basically what's happening is that the light has a certain speed, and the speed is going all the way down there. But when it hits from air to water, water being more denser than air, because we know this, it bends. The light is being slowed down, and because the light is being slowed down, it's bending. And then when it comes back out, it's bended again. So basically, to explain it differently, refraction is when light changes speed due to passing through a transparent substance into another one. This occurs when the light hits the substance from an angle and there is a difference in density between, for example, air and water. This happens because of the time water is denser than air normally. And because this is the case, it breaks and bends towards the normal. So what does that mean? Well, that means basically that air is on top, water is at the bottom, and you have the spoon, and we're already seeing it's bended, right? So imagine we are somewhere here, and we're looking at it like this, right? And imagine that the sunlight is coming in here, but it's then bending because of the density of the water. It's heavier, so to speak. So the speed of the light is being slowed down, thus going towards what we call the normal. Now the normal is basically this one from a straight angle. So it goes towards that normal. But by the time it comes back out, it's, it's kind of been refracted already, to make it simple. So if you've ever taken a swim or tried walking faster in water, you might have noticed the resistance you receive, thus the required energy you must spend to move. It is similar to that logic. The light slows down, bends, and when the light comes back out to our eyes, it has been bended again. because different transparent substances have their own refractive index, which basically tells us scientifically how easily the light will bend. We can use this knowledge to replicate the fact. So we know air has one refractive index, water has 1.33, glass has 1.5, and diamond has 2.44, which is why you can see different effects from different type of substances. So that is refraction of light simplified. And now you know why light changes on these transparent substances and how it affects other objects. So next time you see something is looking weird, you know that the light has slowed down, and because the light is slowing down, we're perceiving it differently. See you in the next video. If you look at this image, you might notice that it has reflection on it. We can see reflection on different places that's occurring. You can see it here, here, here. It's a bit uneven and warped, but it's there. It's even in the spoon that's been refracted inside. But talking about reflection of light happens when light hits and leaves exactly on the same angle towards the same source. And when I say source, I mean, for example, the light hits the water and goes back up in the air. So air is the same source and water is the same source. So in this particular case, the light's hitting and leaving at the same angle towards the viewer, which is the camera from the screen we're looking at right now. So what's basically happening here is that the light's hitting the surface, for example, a mirror or the water, and you have the angle of incidence, which is this angle here, and you have an angle of reflection, which is when it leaves back up to the same surface after hitting the mirror or the water or whatever other surface. Similar to the refraction concept, the incident ray, which is the ray that's incoming from the light source, is being reflected, called reflected ray, and it's leaving the surface towards the viewer. This occurs on flat planes, but also spherical surfaces. I granted that they are smooth and flat. If they're not, they're still reflection, but called irregular reflection, also known as diffuse reflection. In other words, a mirror is a smooth flat surface and gives a regular reflection. A bumpy table, ladder, sofa would give irregular reflection, right? So this would be a pretty smooth reflection, but it's still a bit bumpy because you can see the bumps occurring here. So there are many things that's happening here, but generally the law of the reflection is it needs to hit and leave at exactly the same angle and degree. So it needs to come in 45, leave 45 towards the viewer's eyes, our eyes. So that's why the moon is bright. The moon itself doesn't have any light emitting from it. It's the fact that the light from the sun somewhere else is coming and hitting the moon, and the moon is reflecting about 8 to 12% of the light due to its material and its dark color. It's absorbing most of the light, but around 8 and 12 is being reflected back. In fact, many years ago, the moon tended to be closer, and it also used to reflect much more light, and it used to be much bigger when our ancestors used to look at the moon. But there are many factors that go into how much the moon reflects, but generally it's about 8 to 12% that is able to reflect back to the Earth. And that is why you don't see a completely dark shadows. I mean, technically, if you look here and you look here, you can generally see the shape and the color of your surroundings. And that's because it's still emitting light, and there's still soft shadows coming, and there's soft light occurring. So the key thing is that the angle of incident and angle of reflection are the same measure from the normal line, not the mirror or the surface of your choice. But another thing here is to keep in mind that the reflection of light doesn't always mean literally the reflection. It also refers to something called bounce light, which is basically that the light is being reflected from the moon and it's lighting up everywhere else, right? It's bouncing off the moon, sunlight is coming, boom, and it's coming back here, boom, and it's making sure there's light even when it's dark and late. So I'll see you on the next video. That is for reflection of light. So reflective light, there's more to it. It's not just pure reflection, as I mentioned, from mirror or the water. As I kind of hinted, that when the light hits the moon, it's reflecting 8 to 12% of the light from the sunlight that hits the moon back to the earth, and that is why we have still some kind of light during the night. But another way of thinking of it is bounce light, as we call it. When we do our lighting, we think about how do we add bounce light or fake light or adjust something so the light bounces correctly. So with that I mean is reflected light, or bounce light in this case, as I'm talking about, is basically light coming into a scene, right? There's light coming from different sources, and you can see that it's being reflected, as previously discussed. It's being reflected here, 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 and here, right? But what you'll also notice is the fact that there are hotspots. See the lights, there's some bright spot coming here, there is a bright spot here, and it's all connected to the material, of course, as well. There's a bright spot over there, there's a bright spot over there. You can see there's light everywhere. Despite the light coming from these angles, this whole place is well lit. Basically what happened is lights bouncing around. Because if you take a look at this example, we can see that there's some strong light going on. It's coming from a specific direction. There's more than one, right? There's a light coming in here, and that's because we can see the reflection, but you can also see there is bright spots here. You can also see there is a light here. Of course you can see the light here, you can see the light here, you can see the light here. But you'll notice that the reflection is also here, right? You can see that the color of these materials are being reflected on the ground. You can even see that the color is coming over here. And that's basically, that fact is it's bouncing around. It's not actually just hitting and that's all. It's actually spreading around according to its needs. So basically light's coming there and it's going over there. It's coming over here and it's going over there. Light's coming here but it's going there. Light's coming here, it's going down there. And that's the fact with the bounce light, is it doesn't just hit a particular spot and it stops. It keeps bouncing and it keeps bouncing. Just look at this one here. You can see these are the brightest areas. This is the darkest area. But the fact is, light actually coming in, right? And the light's coming from this direction, so you can see it's coming down and it's jumping around. It's just going inwards and backwards and lighting up everywhere that it can light up. Same is over here. You can see that this is the brightest area, but you can also see there's a light source hitting the wall here. So there's additional light sources coming from this side of the wall. So it's coming in here and it's bouncing. So you can see the bright spot here, you can see a bright spot here. So the light doesn't stop, it keeps spreading around, and it bounces and it bounces. You can tell that in many different ways. Last one here, lights coming in, right? You can see strongest lights, but even then you'll see that the light is in fact jumping around. You can see it goes up, goes back here, goes down here, and you can even see shadow being created from diffused light, or soft light as some call it as well. There's occlusion, as we call it, where light doesn't reach this black. So what does that mean? Well, look at this example in Unreal. Sooner or later we're gonna go into Unreal, of course, and test out everything, but to start giving some more example in Unreal, this is just one light source. It's only aimed towards the sphere, but you can still see that the light bounces everywhere, and it lights up this one and this one. You can even see that it has a bright spot here and a dark spot there, but it's not completely dark. You can see the shape of everything, as well as here. It's not completely dark. You can see the shadow and everything. Of course, there will be more. This is actually terrible, of course. We'll go more into that as time passes. So basically what's going on? Well, let's try and turn this down and do another build very quickly. Unless it's, there you go. It's building light, and it should be darker now, because I'm telling that I want less bounce light to spread around this room that I have made. And the consequences of that is naturally it becomes darker, and it might be unrealistic. It might not be the effect you want. And now it's even darker. Just hold on. So now it's even more darker, and you can see more contrast, more values, and more focus on the sphere. Right? I could do something similar in that maybe I just hit the wall. Let's try building again and see what happens. This video is obviously a bit longer, as you might have noticed, and that's on purpose, because this is very important to understand, that light bounces. It doesn't just hit something, it bounces and it spreads and it catches the color of the surrounding. There you go. Now notice that it hits the wall, but see, there's a highlight still on this sphere over there from the wall. Now, another thing we could do is, if I just quickly duplicate this, and I go in very quickly, and I change the color of this to say red, and I make this like super duper red, apply it, save, right? And I just do annul it very quickly, because I want to make sure that these are in fact white. Right? And only this wall is red. So I'm gonna build again. And I'm building because I'm using something called static lighting. So there's only one wall that's colored, has the red material, and it's all fully valued and saturated, meaning it's the brightest of the red that I can do. And now it's calculating with the color in mind. You can see it's replacing the old one we have. Notice now the room is actually red, because the main light is hitting a wall that's red, so it's casting red. And because it's very saturated, it's also darker now. Now, if I were to exaggerate and say I want 5 indirect lighting intensity, which basically means this light should produce more bounce light to lighten up the room, rather than adding more light sources. So let's build again. What should happen is the room becomes even more brighter. And now you can see that the whole room is red. But the fact is, that's not true. The original material is white, but because of the bounce light and the light hitting a red wall, everything else is catching that color and intensity. And that is what it means with reflected light as well, and bounce light, is that it's catching on the material the color and it's spreading around. As you do this, as we go through the different videos, you will then realize and go, this one light source, it's not that strong, it's only 10 luminance. We'll talk about that as we go. But it's lighting up the whole room, and it doesn't look really realistic now, does it? So that's why you need to adjust it based on what you know, right? To make sure it's somewhat realistic. Otherwise you will end up with something that doesn't make sense. Like this doesn't look good, because we know it's one light source, so we know it's hitting the wall, and it's not that strong. So it shouldn't be lighting up that much. So that's basically what I mean with bounce lighting. So keep that in mind when you do your lighting, or if you have previously done lighting, is if it doesn't look good, it's probably something to do with the fact that the light isn't covering the area it should cover, first of all. Like this is typically how it would have looked from a lot of people when they do lighting. But you'll see a hint of shape if you get closer, right? And suddenly you have a story. So that is it. So we'll see you on the next video. Soft light is another characteristic when it comes to light. That is quite useful to understand, because when you do your lighting in whatever software, really, in our case it's Unreal Engine, you have to be able to understand your reference images and figure out what type of light you're trying to replicate in your software. And one of those things is soft light. And soft light is really can be identified by looking at the shadow. So for example, you can see here it's a soft shadow. Here is a soft shadow, and here is a soft shadow. And generally there's a lot of soft shadow everywhere here. And the reason for that is soft shadow, you can think of it, often it's a large light source that covers a large area, and the rays that are coming from the light source, they are bouncing and spreading and intersecting with each other, and that ends up creating a bit softer shadow rather than a very dark shadow. So an example for that is this image here. You have the light sources on top. They aren't very big, but they can come into the category of area lights. You have light sources in the background as well. Tube light, also considered type of area light in some cases. It can also be identified by the highlight. The highlight tends to be softer and larger. These spots you can see everywhere. You can also see it's covering a lot of area, right? But you can also see the shadows coming. They are fairly dark, but they aren't completely dark. They have the color of the material and they are very diffused. Tube lights are also considered some sort of a light source. They're a bit bigger and the distance is a little bit, so that's also why you'll have sort of a blurred kind of shadows coming from the light source. In some areas, depending on the distance, it will also sometimes be hard shadows, which is also hard light. Here as well you can see that you have many light sources in this image, and you can see the shadows are almost not visible. It's more of a reflection than there are shadows everywhere. That's because of the amount of lights, even though they are spotlights. But you can also see these lights have a filter in front, which basically creates diffuse light, which is not the same as soft light. And because there are multiple sources, you end up having soft light rather than hard light. You can also see soft light is very common to use in photography, and it's very common to use on females because what it does, it creates softer transition on the skin and it doesn't create such harsh shadows, which makes it wraps around your skin, it wraps around the object, so it becomes easier and prettier to look at. Even lit scenes also will end up with quite soft shadows and soft reflections and soft light. Even in with babies, you'll see there are some soft shadow coming, but there is a hint of a hard light coming as well. So these are things to keep in mind with these images here, is the fact that soft light can in fact be considered many things and happen in different ways, but the most important thing to keep in mind when it comes to soft light is the fact that it tends to have very blurry shadows, and sometimes you don't even have visible shadows, like you can not really be sure if this is the reflection or even the shadow in some cases, right? And you can also notice that the highlights are very not as strong, and in some cases there are no highlights, right? It's very dull highlights, it's very difficult to find them. And you will also see that the gradient for them, they wrap around from bright spot to darker spot gradually rather than very fast and crisp. What it also does, it hides the texture, so you can't really tell for sure sometimes if they have a very bumpy skin or not, or pimples or rashes. It's also very difficult sometimes because you can't really know for sure where the light's coming from, like in this particular image or even in this image, even though you know it's coming from here. So that are some of the characteristics of how you can spot soft light. But like I said, there is also something called hard light, which we'll talk about a bit later as well. Another quality of light is hard light. Now, hard light differs from soft light in that it has sharper shadows, but it also tends to be darker. So, arguably, we could say that this isn't just a pure hard light. So, there are issues and situations. Now, look at this image, and you can see that it's receiving quite hard light. You can see that it's dark, very, very, very dark shadows. You can see all the creases and the skin and the details of the face. That often happens when you have hard light. There's also a huge contrast between the shadow and the light. Another way of not thinking of hard light is the fact that you have, again, very sharp shadows on objects, and you have very specific type of light and dark. Now in this room, obviously you have a lot of bounce light and other things happening as well, reflection and so on and so forth as well. Again, you can also have quite super hard light in which you have no visibility except on one side of the face. Outside you often have a different type of hard light as well, because what this different type of light does, like soft light and hard light, is the fact that it tells you a lot of things. It tells you where you are, time of the day, location, atmosphere, mood, place and time, how you should feel, right? Soft light is often used in more colorful images, colorful movies, it's peaceful, it's nice, it's pretty. Hard light, they often creates a drama and tension and contrast. You can see there's it's late in the day, and you can see you're getting some shadow from a tree that's standing probably somewhere around here. Here as well, it's in the morning, it's a bit overcast, but again you have some hard shadows coming from different areas. And again, despite the time of day, you have again hard shadow, and you can also see that you don't see all the details in the darkness here. Here you can see a bit light, and here you can see a bit darkness, and that are some of the qualities that you might get with hard light. So basically what happens with hard light though is that if it's a small light source, like the sun in the background here, because of the distance, it is considered a small light source, and the lights are non-intersecting rays, which means they are parallel, so equal in distance. So what does that mean? It means that the rays have the same distance. You can tell by the shadow as well. And when that happens, you get very harsh shadow, you get small, bright highlights, you get a very sudden contrast between light and dark, right? Light and dark, for instance. Light and dark. Here, because of the reflection of other materials, which also affects the overall look and feel of something, you can still see the brightness over here. Again, light and dark here as well, and you get crisp shadows. But compared to soft light, soft light is when you have a lot of light bouncing around and you don't really know where it's coming from. But in this case, we kind of know there's a harsh transition between the object and the shadow, and we can tell the texture and the details as well because of that harsh shadow. You can see here, we can see the texture and the materials quite clearly. So hard light in life comes from very small lights, such as the spotlights, or very far away lights, right? So you have all different types of light that will create a type of hard light. So point light, spotlight, directional light, tiny area lights are typical lights that we will use in digital context to create all these hard light and soft light qualities. So again, compared to soft light, Soft light has a very soft transition and it wraps around the object so you can see everything clearly, right? So here you can't see everything clearly. Even here you can see there's bounce light. It doesn't mean that it's not a hard light, right? There's a difference between a diffuse light, soft light, and hard light. Here, this is a hard light coming, but it's diffuse light from these that is jumping around the whole scene and creating light everywhere. So that's it about hard light, or also sometimes called hard shadow. Now, hard light, soft light, diffuse light, all of these cast shadow, more or less. But what about shadow itself? The interesting thing with the shadow, as I've said previously, it depends really on if it's a hard light, if it's a soft light, if it's diffuse light. But shadow itself is the absence of light, right? When a light hits an object, right? It's hitting an object, and then it's casting a shadow. That's essentially what shadow does. It creates a shadow shape based on the object. It also means that the light rays are hitting and traveling in a straight line. That's why it's casting a shadow, or a clear shadow. That means if the surface is somewhat solid, it should cast a shadow. If a surface has a hole in it, then light passes through it and it will cast a shadow of the object that has the hole, right? And any object hit by the light through the hole. So in this case you can see that there's a light coming through this window, which is a hole or a doorway, it's a window, and it's hitting this object, and that in return is casting the shadow. Shadow itself though doesn't have a speed. Shadow doesn't actually exist in itself. Shadow is lack of light. In other words, when a shadow moves, the shadow itself isn't moving. The light is simply filling in the area that had shadow. If you happen to move an object over a light source that is creating the shadow, it's not the shadow that's the moving. It's the light and the object, one or the other, that is moving, thus creating the shadow. In other words, during night on Earth, it is just a lack of shadow. But since we have the moon reflecting light, we don't get complete darkness. That means even though there is absence of light, there is still some light entering the shadow, thus creating color in the shadow. If there was no light, there would be no color, right? Because light is made of color, and it reflects, so on and so forth. So light can tell many things. It can tell the shape of the object. It can tell if it's translucent or transparent, right? And you can then, based on that, guess the object as well, and the color, and the direction of the light, right? If the light was coming, the light's essentially coming from this direction, or height, I would say, height. If light was coming from above, the shadow would be over here somewhere instead, right? If the shadow is everywhere and it's hard to tell where the shadow is, that means first of all that the light probably is coming from here. You can tell that based on the hotspots here, here and here, but also you can see that it's this very soft light, so there's soft shadows. They are blurred, they aren't very harsh and clear. That tells me that somewhere here there is maybe a curtain that's blocking and softening up the light to create soft diffused light. Thus you get the soft shadows. Here you can see this photograph. This child is getting almost no shadow. It's very diffused. You can notice it. You can see that there is a soft shadow here, it's soft shadow here, it's a soft shadow here. That tells me, first of all, this highlight over here, which is very spread out, tells me the light is coming from this direction. It also tells me that there is a light source coming from above, because you do see a bit clearer shadow here. So it's coming a bit on this angle over here. Alternatively, I'm guessing there is extra light here. You can tell that by these blue highlights here and here. These are creating the shadows. Two different lights are creating two different shadows for this image. There's the soft light shadow, and then there's a bit harsh light. So different shadow can create different shape, and it can tell us different direction of light, and again can be translucent or transparent. Some are very diffuse and reflective, and you can also then figure out the type of material and the thickness of that object. And then you can also figure out what it's hitting. So the shadow will also be affected, or the light with the shadow and reflection, everything else is also affected by everything else that's going on. In other words, when the light's coming here, it's being diffused not only by the object itself, but also the coffee in it. And you can see there's a blur in shadow. There is a secondary shadow as well. You can see there's shadow here, and there are shadows generally here as well. Learning to see where the shadow tells you the direction of light, time of day. You can see that there is a bit longer shadow going on here, even though these are quite small. They aren't stopping here, they're going quite far out. That tells that the sunlight is somewhat going down, so it's either a sunrise and sunset. And also you can tell by the colors that it's a bit yellow orange, so it's either in the morning or late, right? All of these tells us the quality of the shadow, the quality of the light, and when you put all of this together, you will then hopefully start understanding how light functions and what you can do to replicate it. After all, the light's coming from there, but you see the shadows, right? You see the shadow here, cutting around here, you see the shadows here on the trees. But what you'll also notice is there's a bounce, green bounce light, based on the light spreading and hitting. So it's not completely black either, right? You can see the tree. These are all part of understanding lighting. So that is it for shadow. So the next thing that is interesting to learn about is the inverse square law. That basically means how light fall off over a distance. In other words, as you may see in this example, the light is very strong in the beginning and it fades off slowly until it becomes quite less. The way it works is the further the light has to travel, the dimmer it gets, the weaker the intensity gets. Because the light is spreading out in a larger radius, it also means the amount of light which is equal at any time is being spread out during that traveling. So in other words, if this was 1 meter and this area covered 1 square meter and the light quantity is 1 by 1, the quantity then is 100%. It's 100%. If it travels 2 meters, for example here, it's now covering 4 square per meter. In other words, the light quantity is distributing 1/4. The light quantity is therefore 25%, right? It's just we still have 100% that's being used, but it's covering a larger area. That means in 3 meter, which means 9 square per meter, it's now covering 1/9 of light quantity. In other words, it is 11.11%. That means by the time it reaches 4 meter, it's now covering 6 square meter. It's 1/16, which means it is now 6.25%. That basically means that when the light starts here, it's 100%. As it travels, it's now covering a larger area. And the larger the area, the more the light needs to be spread to light up this area, right? That means that we go from 100 to 25 to 11% to 6.25%. That's why it's called the inverse square law. In other words, if it was a rectangular light in Unreal Engine, it starts very strong, right? It starts very strong, and as it tries to spread itself out, you might notice, you're noticing that this area here is getting weaker and weaker. In other words, it's spreading, but it starts strongly, but it has to cover more area. And you can see some light going on here, but it's very little. That's inverse square law. Again, if I do, for example, a point light, and it's starting in the middle here, the same thing would count, because it's starting here. You see the strong point here in the middle, but you can also see that over a period of time, the intensity of the light source is less. You can see a hot spot here, you can see it's less here, and even less here. And you can see that the light, even when it goes here, it is less. And it's the same concept as explained here, in that as you are traveling a longer distance, the light is then distributed throughout the surface. And it doesn't matter, you can also have the spotlight, and you will see again that as the light hits all these spheres, it's still gonna end up weaker. Of course, in this case, if you want something to be even more drastic and intensified, you can move the light forward, or you can move it backwards, or you can move it backwards and increase the intensity, and then the tenuous radius, and you would get a different effect. But still, you will notice it's following the inverse square law. In other words, if I turn it off in Unreal Engine, you would end up with this. And if I increase the attenuation, you see the light is equal. There's no strong areas, there's no weak areas, they have equal value. And if it's equal value, you might have guessed there is no shape, right? There's no shape. It's flat. You can tell that this is in fact 3D. That is why everything we're talking about is very important, because at the end of the day, that's how you get this gradient, right? That's how you get this gradient effect to tell the story with your light and you adjust it accordingly so you can get some kind of shape to it. And that is basically what inverse square law is. It is distance of the light, and the further the light has to travel, the less intensity it gets. It's very important. So that's it for this video. By now you're probably itching to try some of these things out. That is why we will explain the first lighting setup you should practice and learn. The 3-point lighting setup. In its simplest term, the 3-point lighting uses 3 lights. They're called the key light, the fill light, and the rim light. The key light is generally the most dominant light, and the fill light is the second light source. That's job is to fill in the shadows, and the rim light normally rims out the background and is often brighter than the key light itself. So the fill light, it's hard to be sure which one of these are fill light without the object in the middle, but let's just say that the left one is the fill light. So the fill light is added to lighten up the shadows. So if you're going to light a happy mood or bright mood, a positive mood, or you don't want harsh shadows, you would be having a strong fill light. But if you were going for a dark or dramatic mood, you would have a softer fill light, meaning it doesn't cover up all the shadows. The rim light is often behind on top or right behind, and it generally is to emphasize the backside of a person or the object, so it separates itself from the background, because after all, everything is a 2D image and we're trying to make it look like it's 3-dimensional. So to make it 3-dimensional, we use these 3 methods. In other words, a key light, for example, it would be between 30 and 60 degrees on top, such as this one. So that's the key light, that's the fill light, and that's the rim light. So generally what's going on is trying to hit down on the object, like so. This one is trying to fill in the shadows of the character, because this light, key light, is going to make strong shadows. And this one is filling in it so you don't have shadows, and this one is rimming it so you can see the edges of the person. Notice in general, even in this example without the characters or the person here, you can notice that it's fairly white everywhere because it's an even lighting setup. So if it was a sphere, basically it would look like something like this. So you have the key light, which is fairly dim, coming from this way. You have the rim light, which is this highlight over here. You have, in this case, also bounce light coming here. And you have the ambient light, which you can see here and here. If I take away the ambient light, you see this is how it looks, so you lose part of the differences. So even though 3-point lighting is something you will be using, generally you will be using more than that in the long run. So fully lit, reducing a bit. So notice you're losing colors and details. And if we remove the bounce light, you can see here, you're losing that color and tone and shape. And then if we take away the rim light, you can see that's this one over here. You see now it's becoming more flat. And if you take away the fill light, which is fairly obvious, the shadow, as we said, becomes more harsher, right? It's not as soft, and you only have one light source now. You can tell by the shape here. You can see that the light is it's coming somewhat around here, so it's pretty low. Long shadows is very sharp. And you can also see the cone. So without any lights, if you just use default, this is how it looks, right? So you go from 1 to 6 using different things. So what's going on? Well, as I already explained, you have the key light. So here is the key light, and you can see it's dark shadow and dark shadow here. So you add a fill light coming from here, and then you might realize, okay, you need to make it pop from the black background. So you add the rim light over here, and you might realize, okay, it's need more color and shapes. So you add a bounce light. Let's say it was on a grass or something, and then you might decide we need more environment and ambient, so you add that as well to lit more of the areas. And now you can also see that there is a background and a horizon, so you end up with fairly different mood and tone as well. You can have this one which was fairly semi-realistic, and this one is oversaturated, and you can see by again the highlights as mentioned before, right? And you can see the shadow is slowly coming over here. See the rim light here. Then you can see the cast shadow itself is coming over here, and there's a bounce light coming this way. Here's another one. It's more darker, it's dimmer, you know, maybe it's late on the day or night or afternoon, right? But you still have, you can see that the spotlight source, you can see the difference, right? It has it's over there, but it has a big highlight as well compared to this one. This has a different color and tone. And you can see that it has a different mood. By using these this particular technique, you can still, by playing with color, and color is something we're going to talk about later on after these exercises, you can then have different story, right? Maybe the big circle is a parent, and then there's two smaller kids, one is older, one is younger, and they are talking, right? So you can use different type of color on the light as well to define the story, the mood, and the setting as well. So that's it for 3-point lighting.